has come up for a couple of people. I'm going to open a new file. Okay, so I'm going to actually type in some data here. There's nothing says you can't type in some data. Okay, so the first column is going to be a numerical variable. I think four pieces of data are enough for us right now. So now the next column might be a categorical variable, whatever it might stand for, right? Let's say they have some really odd values, like .d, whatever that might stand for, .r, .d, and just dot. Dot, I don't think these others are going to be a problem. I'm going to go into the variable view, and notice I didn't give it variable names. I didn't type in variable names. In that case, what SPSS does, it just assigns its own variable names, VAR and 001 and 2. Okay. So I'm going to change this to some number, and I'm going to change this to some variable, some category, whatever it happens to be. Notice no spaces, no unusual characters, just letters and numbers. It's got to start with a letter. Okay, the label itself, we can type in a much better description. Some number of interest. Categories of interest. Those are going to be our titles. Now, the numeric variable, okay, now it doesn't know what that is, right? We know that it's a scalar value. We put in numbers there. Now, it recognized that what we put into the second column didn't appear to be numbers because it had letters in it, right? So it automatically guessed nominal and it guessed right. So at this stage now, for scalar variable, we don't put in values. We don't define values because the numbers themselves represent whatever value it is. But for categories where we've summarized what the category is by using a letter or a number or something like that, we now have to tell SPSS what it is, what that represents. So I'm going to click into values, and I'm going to tell it that .d represents, let's see, what can it represent? Shoe size, right? Okay, no, what do I want it to represent? Let's say red hair. And .r represents blonde hair. And now, I don't know what's going to happen when I do this, but I'm going to give it a try. Dot represents all others. Okay, let's see if that works. I'm going to go back to my data view. And, you know, this is very hard to read here. And the reason why it's very hard to read is because since it was only two things there, SPSS assigned only 2 columns to that space. I'm going to move that up. I'm going to make it 16 columns. Right, I'm going to go cancel. Oops. I'm going to go to data view, and look, it spread it out. You know, anything that you change over there has impact on here. So we have some number, some category, blonde, and it recognized all of them. So it actually worked. You don't have to transform the data if you don't want to. It'll actually recognize .d or .r or even just a plain dot as a category. So if you wanted, you wouldn't have to actually transform the data. Now, Professor Renia, to be honest with you, you might want to anyway, because it seems kind of sloppy to use those kind of categories, .r, .d, and so on and so forth. You might want to transform it anyway. Professor Rendina goes through a detailed description of how to do that. Now, one of the things that you may notice where that dot is concerned, remember over here that this first column is a numerical variable. Let's say I skip a row in putting this data in. Person number 5, I knew that they were a redhead, .r, or whatever that one, blonde rather. But you know, and so and the others and the others and so on and so forth. I started to fill in. You'll notice that I can't easily blow this up. SPSS doesn't cooperate that way. But you'll notice that where there's a numerical variable and a column with numbers in it, that if there's no value there, SPSS puts a little dot there. That dot is not the same as the dot in the categorical variable. That just means if it's a numerical variable, that dot means it's a missing value. In the categorical variable, that dot can mean, as an ASCII character, can mean the same thing as most anything else does. That's one of the things might want to be a little bit careful about. In fact, if I do analysis on some numbers, like a numerical analysis, analyze, I'm going to go into descriptive statistics. This time I'm going to go to descriptives, and I'm going to say, oh, this. See, notice it doesn't even bother to put as the category that some category they make the categorical and numerical variable doesn't bother to put it in my choices because it knows I can't do descriptive statistics on those. I'm going to move that into the variables, just frequency. I'm going to move that into the variables, and I'm going to say, okay, let's go to find the average and so on and so forth. And you'll notice that it finds the average. How many valid subjects were there? 7. If I go back and look here, I'm actually up to row 8. It understood that that was not a valid entry, that there's no data there. So it automatically assumed it was a missing value and didn't deal with it. Now, I could have done this a little bit neater and told it in the variable here that a missing value might be represented. I don't know if it'll take a dot. Let's give it a try. By a dot. And descriptive statistics. It's kind of just a little bit sloppy, so I might be a little bit reluctant to really do it this way. But just as an experiment. So we got the same got the same result, and I really can't tell whether it ignored it or realized that that's a missing value. But like I said, when you're dealing with numerical variables and there's a missing, it's just blank. SPSS will stick a dot in there, and that may not really have any specific meaning to what's going on here. So I wouldn't assign any particular meaning. Okay, I think I have something going on in the background. That's why the sound. How's the sound now? Coming out a little bit better? Okay, good. All right, good. Yeah, maybe my internet connection slowed down a little bit. The last thing I wanted to bring up with you is that there are analyses that we haven't gone into yet that are going to be valuable to you that we're going to be doing the next week or two. So I just want to make sure that you understand they exist. Okay, what we've learned so far is that we can do it. First of all, number one, we've learned a lot about descriptive statistics. So you can always, do whatever you need to do in terms of descriptive statistics right now. Your tables, charts, graphs, averages, frequencies, all that kind of stuff. But in terms of interpreting data, we've learned a couple of tests. One test that we've learned is the t-test. And the t-test, we're comparing means. So for instance, one of the numerical variables that we looked at here was the amount of fruit that people eat. So let's see, that was, let me see, how far across was that? One of the other things you can do is once you've decided that some of this data is something you're not going to use, you can actually go through here and you can say, let's delete those rows. Okay, those rows are gone now. Okay, and you wouldn't want to save this without changing the name, of course, or you'll overwrite the original version. Okay, let me see, insured, borough, insured. I'll get rid of this. Cut or clear, either one will work. Diabetes. I'm going to keep that one because we already played with that one. want to see if I can't get to a numerical variable, a real numerical variable here. Smoker, number per day. That's cigarettes, I think. So all I'm doing is highlighting them. I think I'm getting close. This is gender, I guess. We'll keep that one. So you can go through these variables. Oh, what I do here. Oh, I cleared it, but I didn't cut it out. Clearing it just emptied it. Yeah. Again, my version of SPSS seems to be having problems here. Yeah, they're gone. Just didn't realize they're gone. I think I just crashed. I can't move. Yeah, I got really a buggy version of. They've given me the. ICID has given me a really buggy version of this program. What I was driving at was that. Let me see if I can't go into the variable here and still see these guys. Here we go. Fruits and vegetables. Total servings of fruits and vegetables that you ate yesterday. So this data is still here. Okay, so that looks like a numerical variable. I'm going to change this from nominal to numeric because it looks like they're actually telling the number of servings of fruit. Okay, one of the things that I can do is, I'm going to move this up to the top. I can actually drag these around and move them around. And I'm going to go by borough. I'm going to compare the average number of pieces of fruit eaten. First of all, what's the average number of pieces of fruit eaten by New Yorkers in general? So I'm going to analyze descriptive statistics, descriptives. I'm going to go in here and say total number of servings of fruit. I'm going to move that in there. I'm going to click on options. It's going to find the mean, standard deviation. I'm going to click variance, range. Why not? Get all that information. Click OK. And take a look at our output. And the average number of servings of fruit that New Yorkers have is, let's see where it went. Descriptives. Total number of servings of fruit, range to minimum one. Oh, that must be a category because it says it only goes from 1 to 3, right? Maybe it was a different one that we looked at before. Let me see if I go into my data view if that came back. I lost my data view. Oh, wait, here we go. Yeah, it's just categories. I don't know what that stands for. There was another fruit and vegetable variable that we saw before that looked like it was numerical. Okay, let me go back to my variable view. See if we can't find something that's definitely a scalar. What's this is? Place of birth. That doesn't sound like it's numerical. Country. Now, SPSS makes assumptions here. Places of birth, regions, and countries, they might have defined in the code book 100 different countries for places of birth, right? So SPSS looked at those numbers, said, oh, that's scalar, where actually those numbers represent a country. So this is really nominal. So you have to kind of police that a little bit. Nutrition 1, you're right. That's what the variable was. God only knows where that is now. Hope I didn't delete it. You can understand now why we gave you a summarized version of this. There's just so much information here. don't remember going that far in to see it. Oh, God, I deleted it. Okay, no problem. Let me just see if I can't find another numerical variable. Country of birth. Person's self-reported height in inches. That's definitely a scalar variable, right? That's inches. Person's height, that's the 28th column. I'm going to move that up to the top so I can get to it easily. Borrow, move it there. Okay, so I'm going to go to my data view all the way across here. Here's person's height. So that's a numerical variable. I can analyze descriptive statistics, descriptives. I can ask me to give me an average for a person's self-reported height. Click OK. And let's see what we got. Well, let's see. The mean was about 66 inches, about 5'6" tall. Remember, this is self-reported. So I think people are lying a little bit. That seems like a little bit, considering it's both men and women for an average height, seems a little high, right? But self-reported, who knows, right? So the minimum is 2 inches and the maximum is 143. Obviously, there's data in here that's erroneous, that needs to be filtered out. So we know that someone made a mistake in inputting this data if the minimum height was 2 inches and the maximum height was 143 inches, right? So something's wrong with this data. Those are outliers, and there's good reason to think you might want to delete it. But this basically is our average and our standard deviation and our variance for the height of all New Yorkers. Now, if I wanted to compare males to females or break this up by category, I would go to Analyze, Descriptive Statistics, and instead of going straight to descriptives, I'd go to Explore. It gives me a few more options. So I would move in my person's self-reported height, and let's see if people in different boroughs are different heights. I'm going to factor it or break it up, have it do the analyses for statistics, right, descriptives, and perhaps give us a let's see, histograms. It's going to go do box shots automatically. I can ask it to do histograms as well, but it's going to do box plots automatically for me. So I'm going to ask it to analyze, descriptive statistics explore. I'm going to ask it to again give me the average height and those other variables by borough of residence. Factors that's going to break into is that by the boroughs. I'm going to click OK, and let's take a look. And here we go. Got lots more information. So for the Bronx, average height 65 inches. That looks pretty similar, right? Well, people in Manhattan look a little bit taller. People in Queens, a little shorter. Staten Island, a little bit, looks like the tallest, right? That's the tallest average. Looks like tallest average. Looks like it's Staten Island. Well, you might be able to see this data a little bit more and look at, it looks like a fairly good normal distribution in each of the boroughs. Let's look at our side-by-side box plots, which it produced. And here's our outliers. You can see these outliers. Here's somebody that's 7 inches tall. We know that those are outliers, right? And if we look, we can kind of identify what the relative variability in these different boroughs are, right? And there is, it looks like, that Staten Island is the median person in Staten Island is taller than the median person in Queens, for instance. That's the way it looks in this particular data. There's a lot of variability and they overlap quite a bit, right? But we have something of interest here. And notice it used the titles that we told it to use, and it used the for the boroughs. We didn't change the question or the description for the height, so it used that, which actually is pretty descriptive. So I might leave that, right? But we don't have a case where we have number 1, 2, 3, 4, or anything like this. This is a graph you can use almost immediately in a report or a description or something like that. So that's one of the ways that you might use that. The other deal is that one of the ways that we just used this was to use the descriptive statistics to get a look at what this data looked like, to compare the different boroughs. However, if we want to actually determine if a if there's a statistically significant difference between the boroughs, we need to use a hypothesis test. The hypothesis test that we've learned so far, we've learned a couple of them. One of them is descriptors that compare means. We want to compare the means, the mean of the people, mean of the people in Brooklyn to the mean of the people in Manhattan, and so on and so forth. The one that we've learned so far is the one sample t-test. I could say to myself, well, if I had the average height, uh, 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 for all New Yorkers, and I knew that Los Angelinos had a height of 67 inches. I could test to see if New Yorkers are significantly shorter than people from Los Angeles. So it's a single sample t-test. I can click OK, and it will make that comparison for me. It'll run that t-test for me. And let's see, my output window should come up. And here's that t-test, and it found that a very large t-value, and it's a significant result. That's a single sample t-test. We have one sample that we're comparing to a known mean for another population. Let's say they had measured everybody in Los Angeles. We don't often get that. Often we get a situation where we have two samples. We have a sample of people in New York, and we have a sample of people in Los Angeles. In that case, we want to go compare means, and we want to go to independent samples t-test. And in that case, we might put, for instance, we want to compare the people in two boroughs. We would need a variable that has only two values. So let's put person self-reported height in there, and we want a category that has only two values. And we know, for instance, that have you ever been told you had diabetes? I'm going to move that in there. What's this going to do? This is going to tell us whether or not people who have been told they have diabetes are a different, significantly different height than people who have not been told they have diabetes. Now notice kind of a couple of question marks in here. It wants to know what values to use. So I'm going to click on define groups. Remember, value 1 was one group, value 2 was the other group. So I have to put those numbers in so it knows that. I'm going to click OK, and it's going to do that analysis for me. It did that analysis, and it turns out that the mean for people who have diabetes, let's see, is I guess that was number 1. We didn't code that variable. I think that yes was number 1, was 65 inches, 65.4 inches, and the mean for people who didn't have diabetes was 65.9 inches. And SPSS says there. Let's see, is there a significant difference? Well, what we want is a significance here, and that's 0.000, and the t-test is negative 3.6.
It's 10 o'clock.
So it appears that there is a significant difference between the means of these two groups. Okay. Now there's another issue here. What about when let's see, compare means? There's another kind of t-test, and that's a paired sample t-test. That would be the kind of t-test. So we're going to be looking at this in the next couple of weeks. Paired sample t-test is when you comparing two values, like for instance, if we took your blood pressure before you took a drug, and took your blood pressure after a week after you started taking a drug. Okay, and we might have a value before and after for you and for 100 other patients, right? So we would then have two sets of data for each person. We'd have a before and an after for each person. Those are called paired sample t-tests. And we can analyze, some people's blood pressure may have gone up, maybe it's not a blood pressure medication, but we want to know if that's a side effect. Some people's blood pressure may have gone up, some people's blood pressure might have gone down, but instead of looking at it as independent groups, we know that it's really before and after for the same patient for 100 times. So we can make certain presumptions about that, and it'll help us analyze that data. So paired samples is a certain kind of t-test. And finally, there is, this one is called one-way analysis of variance, one-way ANOVA. And that's simply a way to analyze the means of many different groups at the same time. Like for instance, if I clicked on that now, I would move, I might move person self-reported health in there, and I might move borough of residence. And what it will do is it will do a basically a form of a t-test, kind of a t-test. We'll get into more detail for every borough at the same time. It will compare Manhattan to the Bronx and to the Brooklyn and to so and so, and Brooklyn to the Manhattan to the Bronx. It'll compare every possible combination at once, so we don't have to do repeated t-tests over and over and over again for all these different variables. And finally, we also have situations where we want to compare the values of two numerical variables. Like, for instance, does height have something to do with weight? Are they do they correlate? Is there, as you get an increase in height, do you also get an increase in weight? Okay, is there a relationship between those two variables? Obviously, there is, right? But we actually have a statistical test to analyze whether there really is statistically significant correlation between these two variables. And that's called correlation and regression. And we're going to learn about those as we move on to the future. So the reason why I'm telling you this now is because at some point in the future, also the other thing that we are worked with already, also descriptive statistics, was crosstabs, in which we can use a contingency table, rows and columns, right? These are both categorical variables. Rows might be an exposure, like, do you have diabetes? I can put, do you have diabetes in here? Ever been told that you have diabetes? I can put that in there. And actually, I'll move that back here. I'm going to say that's an outcome. I could put borough of residence in the rows as an exposure, and I can put have you ever been told you have diabetes in columns? So you have 5 rows and 2 columns, and we can analyze that using, okay, I'm going to use chi-square, and I'm going to ask it to display for me the observed values, and I'm not going to bother with expected. I'll put expected values. I'm going to hit continue, and I'm going to say OK, and it will analyze that contingency table. Well, what chi-square value did it come up with? It came up with a chi-square value of 30. So that suggests there is some relationship between borough and the frequency of diabetes, right? So that's chi-square. You also, from this here, you can see our expected values, and you can see, see our observed values, 249 and 1348 for Bronx, and so on and so forth, and our expected values. So actually, I'm going to go back here, do this one more thing, and then we'll call it a day. Descriptive statistics, crosstabs. I'm going to go in here, and I'm going to turn off the expected value and turn on percentages by rows. Okay, and take a look at this table again. Again, chi-square comes up the same thing. It finds a significant association between the borough you live in and whether or not you have diabetes. Let's take a look at this. In the Bronx, the risk of having diabetes, relative risk 249 over 1597, is 15%. In Manhattan, it's only 9.6%. Gee, that's interesting, isn't it? Does that have, maybe that's an economic factor? Maybe that's a younger population living in the Bronx. Maybe that's an ethnic factor. Well, you guys might want to play around with that, see what the reason is for that discrepancy, right? This is the risk, right? And overall, the risk is 12.3. So you could calculate a relative risk for the different boroughs, comparing the different boroughs. You could calculate an odds ratio. Odds would have been 249 over 1348, or 304 over 2086, and so on and so forth. So we have a number of different tests. And what drives which test you use is the type of data. This is categorical versus categorical. When we use the t-test, it was numerical by categorical. When we used correlation or regression, it's when we compare a numerical and a numerical variable. So you got a lot. You guys have a lot to learn in the next couple of weeks before we get to the our presentations and our our posters, right? So I think you're going to find it really interesting. But keep an open mind. When you have people's ages, many multiple ages in survey. That's interesting. You have a lot of different ages. I'm wondering whether frequency would be the best way to analyze that. Like maybe one way to deal with that is instead of using a frequency, you might want to use descriptive statistics like mean and standard deviation to describe the ages of people in the group. Or if you want to see if younger people have a higher frequency of something, Liana hit the nail right on the head. That's the next thing I was going to mention. The other thing you can do is you want to see if younger or middle-aged or older people have a different rate of diabetes, for instance, you might convert or transform that data into a categorical data. So, for instance, you might tell SPSS, well, make a new variable called age category, and any age that any subject with an age between 0 and 29, assign that to number 1 in the new category. Any subject between 30 and 49, assign that to number 2. Any value above 50, assign that to number 3, and change it into a categorical variable, which then you can use that way. Okay. You have to go to the code. You have to go to excuse me, Melissa. You need the code book in order to figure that out. Okay. Or if you want to cheat, you can actually just, plot it. Plot the a bar graph. Do a frequency and a bar graph for the that. And you got to figure that more people are insured than uninsured. So the one that comes out higher, I'm pretty sure is going to be insured. But the right way is to dig up the code book and look up what those numbers mean. There's the code book. Is the code book on Blackboard? Yeah, it should be there, right? Yeah, it should be somewhere there with the data. Okay, guys, so let's call it a morning. I'll get this hopefully converted and uploaded before the end of the day. And if you need to go back to it, but I encourage you to go back and rewatch Professor Rendina's videos on the on how to use SPSS and so on and so forth. Yeah, you can group. Well, you can define it as anything you want. Yeah, you could say that. I would just call it by the name. Age 65, 60 to 70, or something like that. Or 60s. Age 60s, age 70s, and whatever name you want to give it. It's now going to be a category. It's not going to be a specific numerical number. It's going to be a category instead. Right? If you wanted, you could call it young, old, and older, or something like that. Give it any name you want. Yeah, by all means, if you go through Professor Rendina's tutorials, especially the most two recent ones, which you can get to on Blackboard, he really goes through SPSS in a lot of detail.